Hello, we're going to begin a new unit on exponential and log functions, and we're going to start off by graphing exponential functions. And so to be able to graph it, we're going to discuss what the exponential function is, and then we're going to figure out if we have a growth or decay, because exponentials can, you can grow something really, really fast, or something can decay really, really fast. We're going to look at some key characteristics, and we're going to look at some transformations, all to help us graph, right? So an exponential function looks like this equation. This is like a parent curve. Every time you change the base, then you get like a new parent curve. But the thing that's important is that b, the base, is a positive number, okay? So our variable is in the exponent. And then the way to tell the difference between a coefficient a and b is that b gets the exponent and a does not. It's just out in front. Okay? So if we look at these examples here, I have f of x equals 2 to the x. A is just 1 because 2 is my base. It's getting the x. And b is equal to 2. In this example here, a is equal to, you can either say -2 or 2. This one is going to be a reflection. We're going to see that in just a few minutes. So I would say a is 2 and b is equal to a half, because the half is what's getting the exponent. And in this equation, a is equal to 1 and b is equal to 1.5. Okay? So in its very simplest application, exponential functions are really an easy way to do repeated multiplications. So instead of going base 2 to the 10th and multiplying 2 like to 10 times, you would just go 2 and then raise your power to 10. All right? But at a deeper and like more useful level, exponential functions are a way to express a relationship when a quantity changes by the same factor over time, as opposed to a linear function where the quantity was changing by a fixed amount over time. All right, we can look at an exponential function and decide whether it is growth or decay, and it's all about the base b. Growth, decay, okay? It's all about the base. So if the base is bigger than 1, you have a growth. If the base is between 0 and 1, then you have a decay. And remember that the base can never be negative. It has to be positive. So in these examples, if we look here, f of x equals 2 to the x. The base is equal to 2, so this is a growth. F of x is equal to -2 times 1/2 to the x. The base is equal to a half, so this is a decay. Here, y is equal to 1.5 to the x. So the base is 1.5, so this is a growth. So on this slide here, what I'd like you to do is I would like you to identify A and B and whether it's growth or decay. I'm going to do a couple of them with you, and then I'm going to have you do several. Okay? So in this first one, I have A is equal to 1.6, B is equal to 3. So because B is bigger than 1, this is a growth. Number 2, y is equal to 3 times 2 to the x plus 4. So my a is equal to 3. B is equal to 2. So this one is a growth. Okay. I'm going to skip down here to do number 5. And so notice here that we didn't do anything with the exponent, nothing yet. We'll get to that in transformations. So you're just identifying A, B, and whether it's a growth or decay. So if we look at number 5 here, we get A is equal to 1, B is equal to 3 over 2. 3 over 2 is bigger than 1, so this is a growth. So here's what I want you to do. I want you to do number 3, number 4, and number 6 as your video questions, and then come back. All right, so number 3, A is equal to 16, B is equal to 0.3 or just 0.3, so this is a decay. Number 4, A is equal to a half, B is equal to 4, so this is a growth. And number 6, A is equal to 4/3, B is equal to 2/3, so this is a decay. The next thing we're going to do is we're going to talk about transformations. These are the same transformations that we've used before. So if you have a negative in front, that's a reflection. It has to be in front of the whole thing. If you have a value of A and it's bigger than 1, it's a stretch. Between 0 and 1 is a compression. Our horizontal shift, if it's x plus h, then it's going to go left. If it's x minus h in the exponent, then it's going to go right. Remember, this moves in the opposite direction of h. Opposite of h. Okay? The vertical shift moves in the same direction as k. So if you have a number back here that's positive, it's going to go up. If that number is negative, it's going to go down. Couple key characteristics. The Y-intercept. All right, the Y-intercept is where it crosses the y-axis. So you plug in 0 for x, and then you evaluate it. So in a parent curve, y equals 3 to the x. If I plug in a 0 here, 3 to the 0, any base raised to the 0 power is 1. So if I plug in a 0, I get out a 1. Now, some people will jump to the y-intercept is 0, a. That is only when you do not have a horizontal shift. If you have a horizontal shift, then it's not going to be that, or a vertical shift, all right? So the critical point is the next important thing that we're going to look at. And the way that we find that, well, what it is when you see these curves, okay, the critical point is going to be that point where it's kind of like in the middle of the bend, all right? So it's like in the middle of the bend, all right? In order to find it, what you do is you take the expression in the exponent, whatever that expression is, and you set it equal to 0. And then you plug it back in to find the y value, okay? So in this example, y equals 3 to the x minus 4 plus 2. I'm going to take x minus 4, and I'm going to set it equal to 0, and I'm going to solve it. Then I'm going to plug 4 back in. So if I get y is equal to 3 to the 4 minus 4. So 4 minus 4 is 0, so I get 3 to the 0 plus 2. What is any base to the 0 power? Well, that's just 1. And 1 plus 2 is equal to 3. So I plugged in a 4, and I got out a 3. This is my critical point. Now, in some cases, like when you don't have any horizontal shift or vertical shift, sometimes your y-intercept and your critical point are exactly the same thing. This one, the critical point, I plug in a 0, and I get out a 1, and so my critical point is also 0, 1. So sometimes the y-intercept and the critical point are the same point. Many times they are not, okay? The last important characteristic that we're going to talk about for exponentials is what's called the horizontal asymptote. It's a horizontal line. It's a horizontal line, and what happens is that the graph out at the arrows gets really, really close to it, but it never touches or crosses it. So we're going to see this a little bit better when we graph, but let me just kind of try and draw you an example. All right, so this arrow, the right arrow, just keeps going up, 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 up. But this left arrow gets super, super, super close to the x-axis, or the line y equals 0, but it never touches it. It gets really, really close, like so close that even our calculators aren't powerful enough to tell us how close we are, okay? But we know from higher order math that it doesn't ever really touch it. It just gets so close, okay? So if what you want to do is you want to look for your k value, because your asymptote is always going to be the line y equals whatever k is, okay? So in this example, y equals 3 to the x. My k is 0, so that means my horizontal asymptote is y equals 0. Here in this example, y equals 3 to the x minus 4, okay? Notice what k is. Here's your k. So k equals negative 4. So your horizontal asymptote is y equals negative 4. So for these, what we're going to do, we're going to find the y-intercept. We're going to find the critical point. Sometimes it's the same as the y-intercept, sometimes it's different. We're going to find the horizontal asymptote and then describe the transformations. All right? So I'm going to do the first one. We have y equals 1.x times 1.6 times 3 to the x. So my y-intercept, I have to plug in a 0 for x. So if I go 3 to the 0, that's 1. And 1 times 1.6, well, that's just 1.6. For my critical point, I have to do it a little bit differently, but in this case, it's going to give me the same value. I set x is equal to 0, and then I plug it back in, and I get 1.6 again. This is one of those cases where the y-intercept and the critical point are the same point. The horizontal asymptote is always y equals k. In this case, we don't have anything being added or subtracted, so we have y equals 0. And the only transformation is that it's stretched, because a is 1.6. Okay? All right. I'm going to do number 2 with you. The y-intercept, I have to plug in 0 for x. All right, so 2 to the 4th, well, that equals 16. And then 16 times 3 is 48. The critical point, I have to set x plus 4 equal to 0, so that gives me x is equal to negative 4. Okay, so I'm going to plug in negative 4. Negative 4 plus 4 is 0. 2 to the 0 is equal to 1. And 3 times 1 is equal to 3. My horizontal asymptote is y equals k. So I get y equals 0. In terms of the transformations, I'm stretched. And I'm shifted left 4. All right, I'm going to do number 5, and then I'm going to have you do 3, 4, and 6 as video questions, okay? So number 5, my y-intercept, I plug in a 0, okay? 3 halves to the 0, that's equal to 1. 1 minus 3, that's negative 2. So it's 0, negative 2. Sorry, this is like looking messy. All right, my critical point, I have to set x equal to 0. I get 0, and then I plug it in. So I get 3 halves to the 0 minus 3. Anything raised to the 0 power is 1. 1 minus 3 is negative 2. So notice that my critical point and my y-intercept are exactly the same because my expression in my exponent is just x. Okay? My horizontal asymptote is y equals k. So it's y equals negative 3. And in terms of my transformations, this is down 3. Down 3. Okay, so why don't you try 3, 4, and 6 and see how you do. All right, for number 3, my y-intercept is equal to, I plug in a 0, and I get out 0.3 to the 0 is 1. 16 times 1 is 16. My critical point, I have to set my exponent equal to 0, so I get x is equal to 0. So when I plug in a 0, I'm going to get out 16 again. So this one is the same. Critical point is 0, 16. My horizontal asymptote is the line y equals k. So that's y equals 0, and this one is stretched. Number 4, my y-intercept is, I plug in a 0, okay, and I just use my calculator on this. This thing becomes so close to 0 that it's ridiculous, that it's like, I don't know, there's like maybe 3 or 4 zeros in front of the first significant digit. So this gives me about 2. My critical point, okay, I set my exponent equal to 0. So that means x minus 7 equals 0. So it's going to occur at x equals 7. And when I plug 7 in, 7 minus 7 is 0. 4 to the 0 is 1. 1/2 times 1 is a half. And plus 2, that's going to be 2.5. Okay? And we can use, I'm going to let you use decimals for this. My horizontal asymptote is y equals k, and k is 2, so it's y equals 2. This one, wow, there are a lot of transformations on this one. It's stretched, it's right 7, and up 2. Right, and number 6, my y-intercept, I have to plug in a 0. And so I get 0, and what's that decimal approximation? Negative 7.4. My critical point, if I take my exponent and set it equal to 0, I'm going to plug in a negative 2. And when I do that calculation, I get negative 14.1. And then my horizontal asymptote is y equals negative 8. And this is stretched, because 4/3 is bigger than 1. It is left 2 and down 8. So now we're going to actually go through some graphing. And the first one is f of x equals 2 to the x. So we're going to identify the base. It's 2. We're going to determine whether this is growth or decay, because it's going to tell us what direction it goes. This is growth. So that means I'm going to be swinging kind of up like this. Okay. A is equal to 1. H is equal to 0. K is equal to 0. Okay. So I'm going to find my y-intercept, and it's 0. When I plug in a 0, I get out a 1. My critical point is the same thing. Okay. Now I'm going to pick a couple points, something to the left. So if I pick -1, and then I'm going to pick 1 and 2. So if I pick -1, 2 to the -1 is 1/2. And 2 to the first is 2, and 2 squared is 4. And so I'm going to plot these. So I get -1/2, 0, 1, 1, 2, and 2, 4. And here's what my graph looks like. And it just kind of goes like this, okay? My asymptote is y equals 0, because k is equal to 0. My domain, the domain for exponential is always -infinity to +infinity. Always. Always. My range, it gets really, really close to 0, but it doesn't touch it, so I'm going to use a parenthesis, 0, and then it's going to go all the way up to +infinity. And my end behaviors, all right, as x goes to -infinity, f of x goes to 0. As x goes to +infinity, f of x goes to +infinity. Okay, let's try another one. We have f of x is equal to 3 times 1/2 to the x. So my base is a half. It's less than 0, so this is going to be a decay. That means that we're going to be sweeping downward like this. Our graph is going to be curving downward, okay? A is equal to 3, h is equal to 0, k is equal to 0. So my y-intercept, I have to plug in 0 for x. So when I do, I get 1/2 to the 0 power. Well, that's 1, and then I multiply it by 3. That's 3. All right? So I'm going to put that here. Okay. And then if I plug in a -1, 1/2 raised to the -1, well, that's 2. 2 times 3 is 6. Okay, you can plug that into your calculator. And then if I plug in a 1, I get 1/2 to the 1 is a half. A half times 3, well, that's 3 halves, or 1 1/2. You can write a decimal if you want. Oops, hit the wrong button. Oh, went the wrong way. This is a 5. And then if I plug in a 2, I'm going to get 1/2 squared. That's a fourth. You can plug that into your calculator. And 3 times a fourth, well, that's 0.75. Okay, so I'm going to graph those points. So I have -1, 6. Then I have 0, 3. Then I have 1, 1 1/2. And I have 2 3/4. And so it's going to go like this. Okay? So my critical point is going to be the exact same as my y-intercept because I'm not shifted. Okay? My asymptote, k is equal to 0, so y is equal to 0. My domain is always -infinity to +infinity. And my range is going to go from 0 to +infinity. My end behavior, as x goes to -infinity. So as I keep going out this way, what way is my arrow pointing? Up. So f of x is going to +infinity. And then as x goes to positive infinity, f of x is getting closer to 0. Last one. Like my vortex? All right. So identify the base. That's a 2. Is it growth or decay? Well, base is bigger than 1, so it's a growth. So we should be sweeping upward, okay? A is equal to 1. What is H equal to? 1. It's the opposite of this, right? And K is equal to 2, right? So my y-intercept, I have to plug in 0. So if I plug in 0, 2 to the negative 1, that's a half. A half plus 2 is 2.5. So I get 0, 2.5. Okay. If I plug in a negative 1, negative 1 minus 1 is negative 2. 2 to the negative 2, that's a fourth. A fourth plus 2 is 2.25. If I plug in a 1, if I plug in a 1, that becomes my critical point. 1 minus 1 is 0. 2 to the 0 is 1. 1 plus 2 is 3. That's my critical point. Notice that they're different here, and that's because we have something other than just an x in our exponent. And then if I plug in a 2, I get 2 minus 1 is 1. 2 to the first is 2. 2 plus 2 is 4. Okay? My asymptote is y equals k. And so this is y equals 2. So here's what I do when I have an asymptote. Make a dotted line because that's what I can't cross. My domain is always negative infinity to positive infinity. My range, I'll fill that in just a second. Let's get these graphed. At negative 1, I'm at 2.25. This is 2. At 0, that's 2.25. This is 2.5 at 0. And at 1, I'm at 3. And at 2, I'm at 4. So it's going up like this. Okay? Just like that. Everything is shifted up. So my range, my smallest y value is getting closer and closer to that horizontal asymptote. So it's going to go from 2 to positive infinity. So your range is going to be affected by your k value. And then my end behaviors, as x goes to negative infinity, so it's going out here, this is negative, your y value, f of x, is getting closer to 2, the k value. And as x goes to positive infinity, f of x is going to positive infinity, right? So these are, that's right, we're going to do write an equation. All right, so to write an equation from a graph, you have to determine 2 points. I'm going to pick this point here, 2, and then 1, 2, 3, 4, 5, 6, 7, 8, 2, 8. And then I'm going to pick the y-intercept, which is 0, 2. All right, so what we're going to do is we're going to plug in the 0, 2. This is what we're going to be working with. We're not going to worry about any shifts or anything, okay? So in order to find A, I'm going to plug in 0, 2. So 2 equals A times B to the 0. B to the 0 is 1, so that means A has to equal 2. Now, it feels like I'm starting all over again. Y equals 2B to the x, and then I'm going to plug in 2 and 8. So I'm going to plug in an 8 for y, and I'm going to plug in a 2 for x. So I'm going to solve for b. So I get 4 is equal to b squared. So when I take the square root, I get 2. I actually get plus or minus 2. However, this thing is going up, so this has to be a positive a, right? So this, because this is a growth, this has to be bigger than 1. And as a matter of fact, it can't be negative at all. All right, so positive 2 equals b. All right, b will never be a negative. It's always a positive. Okay, and so my final equation is y equals 2 times my base 2 to the x. And that's my equation. So you first find a by using the y-intercept. Then once you find a, you plug a and the other point in and you solve for b, and then you write your equation. And here are the problems that we're going to do. If you take a peek at them, some of them are just identifying things. So if you feel like you need to get a start on some of it, go ahead. Thank you for listening.